Welcome to my talk, ReStore, Neural Data Completion for Relational Databases. My name is Benjamin, and this is joint work with Carsten. Many organizations today want to make data-driven decisions. The main tool are analytical queries and data warehouses. And in this workflow, there's a central assumption. The assumption is that the data is complete, meaning that all the queries you expect to query are actually part of your dataset. And traditionally, that was the case, and it was easily fulfilled because the data came only from internal, well-curated sources. So things like internal systems populating your customer and order table. And then, of course, if you query both tables, all the tuples you expect to be there are actually part of this dataset. But today, the resulting datasets are often incomplete, meaning that we face missing tuples in some tables. And the reason is that beyond those basic tables like customers and orders, we also have useful but incomplete additional information. So for instance, tables from open data. So things like customer surveys or demographics, which is only available in some countries and thus incomplete. And there are many sources for this incompleteness in general. You might have systematically missing data. So for instance, it could be that fewer high rents are reported in your data set because landlords don't want to disclose this information. It could be that the data collection itself is expensive because we are dealing with survey data, and that's of course very expensive to obtain a complete data set. And you could also integrate different independent databases or try to augment your data with open data. And that can also lead to incompleteness, as we see next. In this example, we are facing a housing price data set in the US. And we first have a neighborhoods table with state and population density, and that is complete. And this can, of course, easily be obtained for the US. But if you want to gather apartments, this information might only publicly be available in some states due to open data. And that means if you just collect the publicly available information, this means that your data is partially incomplete. So there are few apartments tuples missing for some of your states, and thus you have an incomplete data set. And now if this data set should be used for analytics, this can be problematic because there are two challenges here. First, we might obtain bias. As I said, there could be more apartments from states with a dense population and thus higher rents. So let me give you an example here. Here we only have two tuples in the apartments data set. And if we compute the average rent, we obtain $2,500. However, if we also consider the three green tuples, which we don't have in the incomplete data set, we obtain an average rent of $2,200, which is of course lower. So here we deal with bias. And in general, this leads to inaccurate query results, and we cannot really use it for decision making because we ground our decisions on erroneous data. And strategies, today, this is largely ignored. We simply assume that the data set is representative. However, as we see above, there might be bias, so we cannot safely assume this. And we could also say, let's complete the data manually, but this is a really expensive and error-prone process. So in general, the problem statement we are dealing with in the paper is we want to estimate a query result as if we had a complete database. So we want to estimate this query result given just the incomplete database. And by incomplete database, we mean we have a few tables which are complete, like the neighborhoods table with all tuples, and a few tables which are incomplete, meaning that entire tuples are missing. And now we still want to estimate what would the query result be if we had all the apartments in this example. And for this, we developed a system called ReStore. Here I have an example housing schema with a complete schools and neighborhoods table and an incomplete apartments tuple. And the idea is to use the neighborhood and school tables as evidence to compensate for the missing apartments tuples. So a little bit more detail, we use the evidence in the complete tables to synthesize missing apartment tuples in this example. And for the completions, we of course consider correlations. So for instance, if we know that we have a really high population density and we also see higher rents, we will consider this when synthesizing missing tuples. So we exploit those correlations to come up with really realistic completions. And our approach for this is to learn machine learning models for data completion using the evidence from the complete tables. In particular, I will present autoregressive completion models, and they are based on deep autoregressive models. And I will also introduce additional models that really capture all the evidence in the schema, so-called schema-structured autoregressive models, and they can capture evidence from all the tables in the schema. So for instance, also from the schools table, meaning that we could capture here, for instance, if there are schools with really few students, we might have higher rents. And this gives us even more accurate completions. A little bit more detail. So ReStore works in 2 steps. First, we have an offline step where we learn the respective completion models from the incomplete database, and then an online step where we generate the missing data for given aggregate join queries. So for instance, on the right, we see we want to have the average rent from the neighborhoods joined with apartments grouped by state. And as we can see, we had the 2 red tuples in our apartments table, but we synthesize those 3 additional green apartments tuples to come up with the right result. So as if we had the complete data set at hand. And an optimization is, of course, to cache the data for different queries. Because as I said, our completion is query driven at the moment. In the offline steps, the user has to provide us with the basic information about the schema. So first of all, the user has to declare which tables are complete. So for instance, in this example, landlords and neighborhoods are complete and apartments are incomplete. And there are some additional optional annotations that help us in the completion process. So for instance, here the user might say, I have systematically missing tuples. All the apartments are available for New York City. So as I said, apartments are available fully in some states. And an additional annotation could simply say, this is a partially complete relationship. If the neighborhood is from New York City, all apartments are there. And then what we do in the next step, and this is an automatic step, we generate so-called tuple factors. And for the cases where we know that we have all the apartment tuples, we can now annotate how many respective apartments there are for a neighborhood or for a landlord. And this information will later on be exploited because then the models can roughly estimate how many apartments are missing for the remaining neighborhoods. So this is the annotation and tuple factor generation step. And then next, we automatically learn the respective completion models. And the completion model always takes as input an evidence tuple and outputs a missing tuple. So in this example, an evidence tuple might be one of the neighborhood tuples, and an output could be would be an apartments tuple for the respective neighborhood in this example. And of course, the machine learning models, they really exploit the correlations, as I said. So if we expect to see low rents for low population densities, the models will take this into account. And now the question is, what we use those models exactly for? And the idea is to use those models at runtime to complete joins. Let me give you an example here. So our process is called query-driven completion. And the general procedure to answer a query is we first complete the underlying join, and then we apply filter predicates and aggregations. Because remember that the overall goal in this paper is to synthesize missing tuples and approximate the result as if we had the complete data set. And for this, we first complete the underlying join and then apply filter predicates and aggregations. A simple case is to have only a single incomplete table in a join of several tables. So here we might have a join of states, neighborhoods, and apartments, whereas only the apartments table is incomplete. In the paper, we also discuss the more complex cases where we have several incomplete tables, but for simplicity, we stick to just the single incomplete table case in this presentation. So first of all, we would compute the join of the complete tables, so of state and neighborhood. And as we can see, this is just a normal join that we execute in the database. And then we join the tuples we have left in the incomplete table. So the apartment tuples, which have a join partner in the neighborhoods table. And as we can see, for the neighborhood in California, we don't have any apartments. So what we do next is we predict the tuple factors. Of course, this is only required if we expect several joint partners. But here, for one neighborhood, we of course expect several apartments, so we have to estimate this tuple factor. And as I said previously, for some tuples we know the tuple factor, so the machine learning models can also predict appropriate tuple factors for the remaining tuples. And here we predict, we expect to see 3 apartments, and then we synthesize the missing tuples, meaning that those 3 green tuples are then treated as normal tuples, and then we can just apply any filter, predicate, and aggregation as if we had the complete database at hand. This is roughly the idea. Of course, the magic is how to synthesize those missing tuples. So next I'm going to talk about how we synthesize those missing tuples in detail. The first option that I mentioned previously are the simple completion models, and they are based on autoregressive models. And here our goal is to synthesize missing tuples using evidence tuples as input. So just as a quick reminder, an evidence tuple could be a neighborhoods tuple, and a missing tuple could be an apartments tuple. And for this, we leverage autoregressive models, and they learn conditional distributions of attributes. For instance, they might learn something like, if we see a really high rent, we expect to see a really high rent given a high population density. As you can see on the right, in general, they're structured as follows. We feed in the attributes of a tuple, and then the model outputs the conditional probabilities. So for instance, first, the probability of the first attribute, then the probability distribution of the second attribute given the first attribute, and then last, the probability distribution of the last attribute given the previous attributes. And the idea is to learn such an autoregressive model of join attributes over the join of both the complete tables and the single incomplete table. So on the right, you can see this. We have the evidence tuple from the join of complete tables and the missing tuple. And of course, we can simply join the apartments tuples we have with the neighborhoods tuples and learn such a completion model. And then on the right, we output those conditional probabilities. And now the idea is that we synthesize the missing tuple given the evidence tuple using conditional sampling. So the idea is we first sample the next attribute of the tuple given the previous, the distribution of the previous attributes, and then we sample the second next attribute given all the previous attributes as evidence, and so on. And this allows us to synthesize a complete missing tuple of this incomplete table. So for instance, an apartments tuple given a neighborhood. However, this is somewhat limited. These models, they cannot leverage all the evidence we have in a relational schema. And that's why we introduce schema-structured autoregressive models also in the paper. In particular, they cannot deal with fan-out joins in evidence tuples. So let's consider the example on the right. We have a neighborhoods tuple, and this is an evidence tuple to synthesize an apartment as before. But now we consider a slightly more complex schema. We again have a schools table, meaning that we have several schools per neighborhood. And the problem is you cannot leverage this additional evidence to synthesize apartments, even though it can give you important information. So for instance, if you know schools are really good, then of course the apartment prices will be slightly higher. And previously we had to ignore this because, as I said, for one neighborhood we have several school tuples, but those autoregressive models expect a flat input. So we had to ignore them. And now what we do here is we compute embeddings for the tree structure of fan-out tuples. So let's first consider the first figure. What we could do is we could compute an embedding for all the school tuples we have seen and feed this into the autoregressive model to synthesize more realistic apartments. And in general, if we do an acyclic walk on the schema, we obtain a tree structure of fan-out tuples. And we, in the paper we show this, we use this tree structure to compute an embedding, and we just feed this as additional evidence into the schema-structured autoregressive model. And this allows us to also consider all the school tuples as evidence. And this is much more expressive than simple completion models, and thus also gives us more accurate completions. In the evaluation, we wondered whether ReStore can reconstruct the complete database. And as metrics, we considered first the bias reduction. And this is motivated by biased data sets. It measures how well we can debias a certain attribute X. So 1 is best, 100% means we are just as good as using the complete data set, and 0% bias reduction means we are as good as using the incomplete data set, which is our baseline. In the paper, we also show how well we can reduce the end-to-end query error, but for brevity, we have not included this in the current presentation. We evaluated ReStore on real-world data, and this is really important to capture the real-world correlations and also show how ReStore would work on real-world data sets. And the idea here is that we have two data sets, first a housing data set and then a movies data set with a few million tuples. And we remove tuples of the complete data set and then see how well ReStore can reconstruct the previously full data set. And of course, the question is how to remove tuples. And what we did was we removed the tuples in a way to obtain a biased data set. So for instance, we removed primarily expensive apartments, or we removed primarily old movies. And this gave us biased data sets. But we didn't just remove tuples from one table, we removed tuples from several tables, so from 1 to 3 tables. And in general, depending on which attribute is biased and how many tables we use to remove tuples, we obtain 5 different setups per data set. So in the next plot, we will see 5 different setups for the housing data set and 5 different incompleteness setups for the movie data set. And here we vary additional parameters as well. So we vary the keep rate, and that means how many tuples are left in the incomplete data set from just 20% up to 80%. We also vary the removal correlation, and a higher removal correlation means that we end up removing only the outliers, and we get a really large bias. And as I mentioned, we also vary the 5 setups. And on the y-axis, you always see the bias reduction. And what we can see is, for instance, for the setup M1, that we can achieve a really high bias reduction up to 100%, which is as good as if we had the complete data set at hand. In some other cases, we have lower bias reductions, but please note that we are always better than 0%, and 0% is just as good as the baseline of using the incomplete data set. So we never saw any regressions of using ReStore versus the incomplete data set. But as you can see, the accuracy varies, and the reason is that some attributes are easily predictable given the evidence, and some don't really correlate with the remaining evidence tuples we have in the data set, and that's why we cannot easily reconstruct the full data set. And that's why an interesting question is, can we recognize the cases where the completion will be really good? And that's why in the paper we derive confidence bounds also. So the models basically give us an estimate on how accurate the current completion is and give us a confidence interval similar to approximate query processing. And the details can be found in the paper. And as a summary, we've seen that incomplete data is everywhere, and we cannot just ignore it because we have so many sources of incompleteness, and we will likely end up with biased data sets and thus inaccurate query results. So for instance, again, the query on the right, if we want to compute the average rent grouped by state, we might end up with erroneous results if we just take the incomplete tuples. And that's why we developed ReStore, which estimates the query results on the incomplete data set on the right. So on the right, we synthesize the missing tuples given the evidence of the complete tables. And as we've seen in the evaluation, we obtain really promising results on both synthetic, so the details are in the paper, and real-world data sets. And in the paper, we also consider really complex cases of multiple incomplete tables and all the details on the models. The code and data is available on GitHub, so please feel free to experiment with it. Thank you for your attention, and now I'm ready for questions.